So as you can see, we have the learning targets up here. This is all coming back from our spring lab that we also did as well. As we go through this, you'll see that I'll always come back to these 5 learning targets. My plan is to try to get through the first 4 today, and number 5 will be homework, coming up with the general equations for other common forces here. So with that said, number 1 talks about the relationship between Ft and x for a spring. So if we were to look at this, one of the things that we can do is look back at that graph of F versus delta x. So we can go back and draw in that graph that we had, and if you remember correctly, you had Ft sitting on over here. It's a horrible Ft. Let's try that again. Ft, which is sitting on over here, delta x, which is sitting right on over here, and we saw 2 different types of graphs. Well, we're going to talk about 2 different types. The major one that we're going to put our focus on is one that has a y-intercept of 0. So anytime you have a y-intercept of 0, this is what we call an ideal spring. This is the one we actually care about more than any of the other ones. This is the one that we will use. This is the one that we will always assume. Any non-ideal springs have a y-intercept. That means it takes a certain force to actually get it to stretch. Don't worry about that in this class. However, if you do advance further on into AP, you might run into situations like that. The next thing that we talked about, we looked at yesterday, was the slope. If you remember correctly, the slope is what we are going to call as the spring constant, K. K, again, refers to the spring constant. And with that, this is also known as, you could call it the strength of the spring. Heavier duty springs, like the spring I showed you yesterday, the couch spring, has a larger spring constant than other springs, the ones that you were using in your lab. So that spring constant K refers to, again, how many newtons it takes for it to expand or contract a meter. From this and looking as a whole, what we can do is we can finally get the equation that we developed yesterday, which is for any ideal spring, you can say Ft for a spring is equal to the slope times what's on the x-axis, in this case, delta x. So this is for an ideal spring, so this is force of a spring. And K is, again, actually I could be tricky and I could go like this. K is going to be our spring constant, and delta x in this equation is going to be the stretch, as we saw in our lab, or the compression. Springs can also compress. They also follow the same exact formula as well. So anytime you are looking to calculate the force by a spring, you can go this route in order to solve it. So this does sum up our first target here. Understand the relationship between Ft and x for a spring. Is there any questions? We'll be looking at worksheet 2 point something that is going to help us understand this target. The next thing that we need to look at, and this was actually our other main goal for the lab, is to determine how to calculate the energy transferred by a spring. So in order to do this, let us take this to the next step and say, all right, how do we calculate ES? So let's go back to the graph here of Ft versus delta x. And my first question that I have to ask is, wait a minute, hold on. As I continuously stretch the spring further and further, what happens to the energy? And the answer to this question is, as you stretch it further and further, you are storing more energy into the spring. So as delta x, if we go back to our graph here, as delta x increases, as we go further and further, there is something on this graph that increases as well. And that something is the area. And so when we finally get in here, what we can do is we can, let me be a little fancy here and pull out a red color here. What we could do is if we wanted to calculate the energy stored in the spring as you stretch it, all what you have to do is you have to calculate the area that sits in here. So this area represents ES, the energy stored in the spring. So at any given moment, if you stretch it, you can see how much energy the spring has stored in it purely by looking at this graph and taking the area there. Question, yes?
Do we ever have a curve where we have to find what's underneath it?
We are going to examine more and more different, actually let me repeat the question just in case. Question was, are we ever going to run into curved F versus delta X graphs? The answer is no, not in this class. However, if you get into calculus or other aspects and you run into a curve, all you have to do is take the integral and you can get that. For this class, you will see our two shapes that we will run into, rectangles and triangles, which hopefully you can calculate areas for those. Yeah, mind explosion. So, good question. And as you can see as one of our other targets up here, I can come up with general equations for other common forces. Any force that you look at, if it is a force across a distance, if you take the area of that graph, you are calculating the energy that is being transferred by that force. And we will examine that a little bit deeper as we go. Now, of course there comes an equation with this. Of course we can actually break this down a little bit further. And a general equation, and this is general but it's a little bit more specific, is actually taking the area of this. And so ES is going to be the area, and the area is going to be, of course, for this shape, 1/2 times the base times the height. And we can be a little bit more detailed about that and say, well, we have 1/2. The base in this case is going to be delta x, and the height in this case is going to be ft. Now, this equation works as long as you start stretching at 0 meters and it is an ideal spring. Those are the two assumptions that we have made with this equation. But it works. The other way that you can look at this is again ES for that specific situation. The other thing that we can look at with this is FT. If you guys remember correctly, we just developed an equation for FT right up there. So we can perform that substitution, and you can see ES. Let me actually make sure that is an S. ES is again, well, we could do 1/2 times delta x, and then you'll see ft is actually k times delta x, and you realize that we could start combining like terms, and we come up with our general equation. ES is equal to 1/2 times k times delta x squared. Now again, I box this in, and I always say be very careful with, again, using equations. I like this equation, but it stands for two specific cases. The case is, what assumptions have we made? Well, if I go back to this, the first assumption that I've made is this is an ideal spring. Again, this is assuming y-intercept of 0. The other special thing for this exact equation that we're seeing here is we are starting at 0 and we have gone to a specific point that is delta x. If we don't start at 0, this equation does not work. This is only working if you start with a spring with 0 stretch and then you stretch it out from there. So that is how this equation works. That is the way that we can look at it. So again, we've just get the idea here. We have just done number 2 as well, so you can see 1 and 2 are off our checklist here. The last little bit that I want to talk to you guys about is the units. And the units for this is kind of twofold. you can see, and the way that we are going to break this down is the units for energy. I'm going to use this equation right here because it's probably the simplest. The units for ES, or any energy in specific, is going to be, well, you see 1/2 is unitless. The unit for delta X is going to be what, in most cases, we're going to see a meter, and the unit for FT is going to be a Newton. And so what we get out of here, and it's most commonly pronounced Newton meter, so just rearranging those two, is going to be the unit for energy. However, if you just keep saying Newton meter, Newton meter, Newton meter, you're probably going to get tired, and they have shortened it, and this is reflective of something that we have seen before. In chemistry, this is a J, or a joule. So this unit of energy works directly, let me write that a little bit clearer for you, with what you've seen in chemistry as a joule. So, as you can see, we've just knocked out target 3. And in target number 4 up here, it says, I know how to calculate the energy transferred by a force. What we have really done here, and this is the final general main idea for this lesson today, the big thing is to calculate the energy transferred by a force. So, to calculate energy transferred by a force, in order to do this, we take the area of the force that we're dealing with, versus delta X graph. The moment you do this, you have your energy transferred by that specific force. So as you can see, we knocked out those 4 targets up here. The main ideas, 1, 2, 3, 4. Your homework for tonight will be number 5, which is I can come up with general equations for other common forces. There's forces like force gravity. And one of the things we're going to see is if you can draw a force gravity versus delta X graph, that means, again, if we go on over here, a force gravity versus delta X graph, if you could draw a good one of these and then look at the area, you can come up with an equation that can give you EG. Yes, question?
Are you able to do this on Earth? Because wouldn't you have to go somewhere else to change the gravitational pull?
Well, this is a really interesting question. As you change delta X, let's go over this. As you change delta X, what happens to FG?
Well, like if you're going up and down?
If we're moving an object up and down, what happens to FG?
By Einstein's theory?
By the being close to this is a good question. No, we are not going to go all the way into the realm of Einstein or Newton in this case. We're going to keep it simple, and we're going to say near the surface of the Earth, as you increase the height, what happens to FG?
It doesn't change.
It stays the same. So as I increase the height, what you're going to realize is, how is this graph going to look? It's going to be a nice straight line like that. And so with that, then you can rope off the area and you can actually calculate EG based upon this. So it's a very simple, easy, quick way to calculate energies if you know the force as delta X changes. And we're going to play around with certain examples in worksheet number 1 in order to get this idea.